Hello, everyone. My name is Frisk, and today I'm going to talk about DMA abuses and in-memory malware detection. You might went to Disabay earlier this year and saw my talk live memory attacks and forensics. And I will have plenty of new stuff in this presentation, but you will also remember some slides. So I'm going to start by doing some live memory DMA attacks with PCILeech. I'm going to DMA using an FPGA hardware into Windows. And after that, I'm going to attack Hyper-V Linux virtual machines from the Hyper-V host itself. Then we'll jump into live memory analysis with MemProcFS. I'm going to analyze a 128 gigabyte live running machine in just a few seconds. And I'm going to find some evil in a memory dump from this OBE Memory Forensics workshop. And then we'll look into some API stuff as well. So who am I? My name is Frisk, and I'm working as a pen tester by day in Stockholm, Sweden. And I also try to do some security research and open source development by night. I'm the author of the PCILeech and MemProcFS tools, which are pretty much my hobby project. So I presented this at quite a few different cons, including Disabay earlier this year, but also DEF CON Blue Hat and the CCC. And everything that I've been doing up until now has been like 100% open source. So this is how my two tools, PCILeech and MemProcFS, relate to each other. We have the PCILeech, which is more geared towards the offensive side of things, the red team side of things. Insert an FPGA hardware in your victim computer, and you're able to read and write memory, insert evil kernel modules, take control of the system, bypass BitLocker, and stuff like that. Then you have the MemProcFS, which is high-speed memory analysis and memory forensics. And this is more helping for the blue team, I hope. So they both use the same backend library, the LeechCore library, which allows me to abstract physical memory access in a really nice way. So it doesn't really matter whether I'm using an FPGA hardware device to acquire memory, if I use a loaded driver into the running system, or if I use some memory dump file to analyze. So what makes the hardware attacks possible is something called DMA, direct memory access. And PCI Express devices, they have traditionally been able to access the main memory straight out, no restrictions at all. A PCI Express device is able to read the main memory without passing through a CPU core. And this is what makes PCI Express so fast. This is really unlike how it's looking at the code side of things when code is running on the CPU. Code is executing in virtual address space, and you have something called the memory management unit, the MMU, in between, which is doing translations from virtual addresses into physical addresses. And this memory management unit is pretty much what upholds the security in modern day computers and doing process isolation and things like that. This CPU vendors, they introduced something similar, an IOMMU, in the CPU designs like 10 years ago or something like that. But as we will see in some demos today, this IOMMU is not really fully used in all setups still today in firmware and operating systems. So it's still possible to do DMA attacks in some extent. But you also need PCI Express, and PCI Express is kind of lots of things. You have the ordinary PCI Express you use in your desktop computer, your graphics card, if you're doing gaming, is like PCI Express. But you also have quite a few other different form factors. The Mini Express and Express card is for older laptops. It's not so common nowadays. Thunderbolt is really common. It's pretty much external PCI Express, but it's quite well secured for most parts nowadays. So it's a little bit boring for these kinds of attacks. You have the M2KM, which is for disk drives nowadays. It's also PCI Express, and the M2KA plus E. It's really common if you pop the back cover on laptops, you will find a Wi-Fi card there quite often as this form factor. So this is how it's working. On my analysis computer, I'm in software, I'm creating something called a PCI Express transaction layer packet. PCI Express is packet-based. And then if I want to read memory, I need to create a memory read packet. Then I will transmit that one on towards the FPGA over USB 3. And then the FPGA sees this memory read packet, and it places it on the PCI Express of the target system, the Express card in this case. once the PCI Express TLP reaches the root complex of the target system, it sees that it wants to read some memory in this case. And then it reads the memory and responds with a completion packet containing the actual data, which is then transmitted back to the FPGA and forwarded back to the analysis computer. And this is how we're able to do both memory reads and writes. So I'm going to start with a recorded hardware demo. It's kind of hard to do like hardware demos live on a live stream here. So I'm going to switch over to a video. So this is a desktop computer. And you see the screen to the right and the computer to the left, and the attacking computer is the laptop. We tried to log on to this computer without using a password. We were unable to do that because this user has some password. This is pretty boring, so we want to change this. We don't know the password. We want to break in here. It has BitLocker on and things like that. So we quite often you can on computers you can do sleep. If you click in the right corner and you do sleep, which is suspend to RAM. RAM is still active, but the CPU is shut down and the PCI Express is shut down. And this will enable us to insert the evil PCI Express device into the computer without the computer freezing or anything like that. And then we just press some button on the keyboard to unsleep the computer. And we will try to log on again, and we will fail again because we haven't really done anything except inserting a hardware device. So now I'm connected with this attacking computer to over USB-C, and I'm running the PCILeech dump because dumping memory is kind of nice doing because there are lots of things in memory. For example, you have the BitLocker AES key floating around in memory. You have lots of other things as well, passwords and things like that if you're lucky as well. And we're starting the dump here. It's kind of slow in this demo. It's around 80 to 100 megabytes per second. I think it's because the disk drive on this attacking computer is a little bit slow. So usually it's around 150 megabytes per second. But yeah. So dumping is going to take a while. So I sped up this video a little bit. So you see a jump here soon. Yeah. And as I mentioned, there's lots of like credentials and other interesting things in memory. You maybe want to do some memory forensics, and it's a good idea to start with a memory dump, I think, because you will preserve a lot of things in memory before poking around and changing stuff. So we'll wait till this is finished. And then we'll try to log on again. And we'll try to log on again. And it's still failing because we haven't done anything really. Kind of recently, I got a really awesome contribution called Pushpin, which is a GUI for PCILeech. PCILeech is a command line based tools, and you can do lots of things on the command line, but it's kind of nice to have a GUI. Just drop it in the folder of the PCILeech, click a button to insert an evil kernel module into the running Windows system or the Linux system. You have code execution in the kernel now. And then you click a button for unlock as well. And you'll see if we can log on to the computer without the password. And we're in. So let's continue to the next demo. For the next few demos, I'm going to be using Hyper-V virtual machines, and I'm going to do it remote over the network. So my network is like this. I have an Active Directory. I have a demo client running the PCILeech and the MemProcFS. And I have a Hyper-V server, which I have installed a leech agent on, which is part of the PCILeech toolkit as well. And from the client, I can connect over an encrypted mutually authenticated RPC connection, which is secured by Active Directory Kerberos, and do stuff remote on this Hyper-V server. And then I'm going to use something called Live Cloud KD. It was something was initially created by Matt Swish a long time ago, but recently it's been taken over by a guy that goes under the name Gerhard X on Twitter. And that basically allows me to load a driver into the running system, and then I will be able to access both read and write the virtual memory of the memory of the virtual machines running on this Hyper-V machine. And this is really convenient when doing demos today. So let's demo how to unlock a Linux machine from the Hyper-V host. So I'm going to be switching to the Hyper-V host here, I hope. Bear with me. Yes. So where do I have everything? So many. Yeah, here I have it. Yes. So sorry for that hiccup. So this is my Hyper-V host, and here I have some machines running, a Linux machine, and this is a Ubuntu machine, and try to log on to this machine with a password of ~A here, and we will fail because there is some other password on this machine. So let's switch to our demo machine, and here I'm going to run the PCILeech. I hope you can see this on the screen, everyone. I'm going to connect to the device HVMM, which is the Live Cloud KD, and I'm going to connect over an RPC connection. And I'm going to insert a kernel module into the Linux system here. Need to select which virtual machine to attack. Takes a while for it to connect. And now we're searching for the kernel. We have code execution in the kernel, and we inserted an evil kernel module into this Linux system. Now we can do things. We can use PCILeech to mount the file system, and then we need to specify the kernel module address as well, because it needs to be executing some code in the kernel to read the file system of the Linux system. So we connect to the virtual machine again. And it says it's mounted as the K drive. And if we check into Windows Explorer now, you will see it's mounted in a K drive here. You have the live RAM. If you want to do a memory dump, you can actually copy the files from here in Windows Explorer as well. Or you can click into the files folder and you have the whole Linux file system here. You can even do things like doing some hex edit stuff of the raw disk devices, because in Linux, pretty much everything is a file. And you see, like, we have some grub data here. And so let's not destroy the disk. Let's do something else. We want to break into the computer, right? So in Linux, we have a really interesting file in etc. We have a shadow file, which contains the actual password hash of the user here at the end. And this is, yeah, we can try to crack this one in Hashcat if we do wish to do that. Maybe the user has a bad password, but if we have this kind of access, it's easier to just replace the password hash and hit save. And once we've done that, we can try to log on to this Linux computer again. And remember, this attack also works if you're using the FPGA hardware. And as you can see, we're hopefully logging in here. Yes. So let's continue. Let's talk about the memory process file system, MemProcFS as well. It's really memory forensics done in a completely new, different way. So I wanted to create something that was geared towards Windows memory analysis. It allows you to visualize in-memory objects as files and folders in a virtual file system. It is multi-threaded, it's coded in C, and it has some really intelligent parsing in there, which makes it like super fast. And it do support both hardware memory acquisition with the FPGA devices, but also software-based memory acquisition and dump files. So why do you want to do memory forensics? It's kind of important to capture running state of the system, like running processes, network connections, and other things that don't really exist on disk, because disk forensics doesn't tell you the whole story. For example, you might have in-memory only malware injections into processes and things like that. Also, crypto keys might be in clear text in memory, but encrypted on disk. And it's also faster than doing disk forensics. You only have to work with a few gigabytes instead of terabytes. So let's do another demo. Let's pop a Windows machine using both Mimikatz and IDA, and we're going to attack a machine with 128 gigabytes of memory. So let's switch to our Hyper-V server again. Here I have another virtual machine, and it has a really big memory size here. It's like 128 gigabytes. And if we switch to this one, you have the John Smith user here. QWERTY123456 is the password. Let's try that. And yes, we can log on to that. But let's pretend that we don't know the password and we want to change this password. So let's switch back to the demo machine. So I'm going to switch over to the MemProcFS now. We're going to be connecting over the RPC again to this remote Hyper-V host over the network, but we use the MemProcFS now instead in order to mount the memory itself as a file system. So we need to connect to this Umbrella Corporation machine, and it says that we are connected. And now I can actually go in and have a look in the file system. In the root folder, I have things like the memory itself as a dump file, Microsoft Crash dump file format. You might want to do some win debugging on it. I have folders. Each process is going to show up by name and PID in these folders. And if you want to attack it, we have a process that is really interesting. It's called LSAS. As you might know, it's the password vault for Windows. It was like Mimikatz is attacking. And in this, for each process, then I have a couple of files and folders. You have the virtual memory. You can go in and edit it straight out if you wish to do it with your favorite text editors, some other information files. But I also have a minidump folder here. And minidump files, it's what you create if you're running Task Manager, and you might want to create like a dump file. And if you do that on LSAS, you can actually use Mimikatz on it. So let's use Mimikatz against this live Hyper-V virtual machine. So let's start the Mimikatz, and we're going to be attacking process 956. And it says that we switch to the minidump here, and now we can run the secure LSA logon passwords to see what we can find in memory here. Seems like you found a lot of things. If we scroll up here, we see this John Smith user. He has some anti-LM hashes and things like that. That is really nice. But he also had the WDigest authentication provider enabled, and that allows us to see the password recovery in clear text as this user was logged on. So this is one way of doing it. We might want to use IDA to do some live patching of the memory as well. So in LSAS, we also load like lots of DLLs and modules inside it. So and one module that is called NTLM shared is responsible for the actual password verification. So when you type in your password, it needs to check it against a stored password hash and see if it's equal, then you're logged in, and otherwise it will fail. So let's open this with IDA, and it needs to create some temp file here. So just put it there. And I do the default and download the symbols from the Microsoft Symbols server. And I know the function is called MSVP password validate, I think. So this is a really big function. It's really complex, but it all boils down to it's doing a lot of checks and things like this. But it hashes the password that the user is typing in on the console, and then it's like doing a memcompare in the end. And it's actually doing the memcompare here. And then it checks the result of the memcompare. If it's failing, it will throw up like you're not logged in, it's the wrong password, otherwise it will log you on. So if we check this jump 0, that it is right now, we see that it's 0F84. But I know that jump not 0 is like 0F85. So what happens if we like just invert this to a jump not 0? We can patch the program, change a byte. We change the 84 to 85 and press OK. And then we need to apply patches to the input file. And then the MemProcFS will automatically write this over the network to the remote Hyper-V machine. So let's check if we can log on to this remote Hyper-V machine now. So we knew the password now from Mimikatz, right? So it's 30123456, like this, and we know it's just before, but it's not working. And this is because we inverted the password check. So if you just try any other password, like no password at all, we're getting logged on just like this. So how is MemProcFS working, and how is it designed? So when I created the MemProcFS, I wanted to have something that was really easy for the user to use. It should be able to click around in an easy to use file system. I wanted to have the design really modular, have plugin functionality, so you could code your own plugins and just drop it into it. I wanted to have APIs for C and C++, and also Python, because Python is really easy to use. And later on, I added C# as well. And when clicking around in a virtual file system, you want it to be fast, performant. You don't want to wait a couple of minutes for something to happen. You want it to be instant, or actually, even if it should feel instant at least. So this is how the design in modules looks. I use a third-party real awesome product called, it's open source, it's on GitHub, called Doken. And it takes care of the virtual file system part. And then the Doken calls into my MemProcFS executable, which is a really thin wrapper around the main analysis library, which is the core of things. I have external plugins in both C and Python. And on the back end, I use this Leech core library to abstract the physical memory access. So on the very top of this library, I have the API, C++, it's coded in C, so that one is given. Also have a Python API, and as I mentioned, a C# API. On the very bottom, I have an object manager, a custom-made one that allows me to do things like object reference counting, and this allows me to do multi-threading in a really nice way. I have caches for both physical memory and the page tables, and caching is super important because we want to have performance, and accesses to disk and live memory is a little bit slow. Then I have a layer doing virtual to physical memory translation. I support the normal like Windows memory models. I want to add ARM here as well, but I don't think it's that common on Windows yet, but it's definitely going to be something for the future. And I have my main analysis layer. So I have various kinds of memory analysis tasks. You want to analyze whatever stuff. I have the notion of a process object, and inside the processes, I have other objects for something that I call maps. For example, like the memory map, you have something called virtual address descriptors, and you have the loaded modules, as we saw in the earlier demo with IDA, the DLLs. Also support plugins, and plugins can either be external or internal. Actually, there's like lots of internal plugins in the design for this, and then have worker background threads, which are doing some background tasks to speed up things for the user. So we can actually use the MemProcFS to find evil as well. And now I'm going to switch back to the demo computer again. Now we're going to be doing some demos against, if you visited Disabay earlier this year, you might have taken the Memory Forensics class actually. And I didn't do it, but they have a really awesome memory dump there. So I'm reusing this one now. So you might be, so basically I can just mount the memory dump by double clicking on it. And it says that it's mounted as the M drive now. So let's click into the M drive. And here I have a couple of directories. We have the MISC directory, which I have some find evil functionality, which is basically parsing the memory to find things, telltale things of like injected DLLs and things like that. It might be a little bit slow to load here. It's like 93% done only. So let's do another refresh and it seems to be done. So it's still quite all right, I hope. So when we open this, it has done memory analysis on all processes to find like irregularities between these different memory maps. And it sees that we have something that is injected in Windows Explorer, some net.srv.dll and some other evil looking stuff as well. If you scroll down a bit, we have some patched binaries. Unfortunately, this is going to be some false positives as well. We have something called relocations that will feed into this as well, that I need to find a good way to suppress without like suppressing good findings as well. Then we have read, write, execute memory, private read, execute memory. And this is really bad, usually. And it's in Windows Explorer, so I suspect it's related to those earlier malware or injection stuff. And then I have some funny looking process name here. It seems to be pretty, this is like malware looking as well. So let's take some notes of this, I think. It's always good to keep some quick notes when doing things. And then let's continue. You have another folder, which is called the forensic folder, which is, we need to enable like a forensic mode, and this is going to do a full scan of the memory image. And I only enable this when you're doing against a memory dump file. And we have a couple of modes to enable it. And I think mode number 4 is kind of nice because this will create a SQLite database on disk, drop lots of forensics artifacts in it. You can open it in SQLite itself and also use this database to click around in the memory. This is going to take a while, so let's explore some other things. As well, we have a folder called sysinfo, which contains various system information, which is not really related to a single process. For example, we have the certificates. Malware might inject like a fake root certificate to do man in the middle. Network connections are always interesting when doing memory forensics. And if you check this one, if you scroll down a bit, we have this funny looking process name again. The malware looking one, and we have some connections here to port 4444 on a remote host. And this is like clearly suspicious, and this might be a good IOC actually. If we find out that this is a malware, this might be a CNC server or something like that. So let's take a note about that, this one as well. Process listings are also kind of interesting. If we check in a process listing, and here we see lots of processes, and we have a logged on user here. It seems to be like the logged on user is Dustin Henderson here, and seems to be pretty normal. Star is something without the outside the normal Windows paths. So that might be interesting. If we scroll down here, we see the C script. And this is spawning like 2 of these funny looking malware processes. Looks kind of interesting. We have some calc.exe here as well, some misspelled calc. Outside is a star marked as well, so it's not from the Windows directory. And we have an Internet Explorer, which is not running from the Windows directory either. So this is all kind of interesting. So let's open it in verbose mode as well to have a closer look. scroll down to the end to these funny looking processes. We have this malware looking stuff that is spawned by C script. And if we look at the C script, we see actually it's spawned by some DBS file here. And this is interesting. So let's take a note about that one as well, the C script. And we had this Internet Explorer as well, was kind of interesting. We see that the Internet Explorer, it's actually spawned by the Dustin Henderson. It's app data local temp. And this is like clearly not Internet Explorer. This is something that is trying to mask as Internet legit looking process or something like this. So this is going to be interesting. So let's close this once and let's check back to the forensic mode, see if it's finished. It seems like it's finished now. And I do both something called timelining, and I'm also trying to parse the NTFS MFT in a nice, convenient way. And the forensic mode is doing one big scan of memory, and then it's doing multiple analysis paths in parallel to speed things up. But if we wanted to look, we look into this Dustin Henderson guy, we check his app data local and see if we can find some interesting things in his temp directory. So we can click into the NTFS users, Dustin Henderson, app data, local, temp. And here we had lots of interesting things. We have the iExplore.exe, we see it there. I have this listed as in a single file as well, if you wish to. I have some inquiry docm, and docm is like for the macros. I have the file size here. Unfortunately, when doing a memory forensics on the MFT, it's not possible to recover the actual contents of the file unless it's like really, really small, like a couple of 100 bytes. And if it's really small, you can actually click on it to open it. And you see the VBS script here as well. So it might be convenient, but you get a nice feeling about how the file system looked, at least. Then we can do something called a timelining as well. So basically, I'm taking all the forensics artifacts on the system and puts it in this SQLite database, and then I generate everything by timestamp. So this might be a little bit interesting. We need maybe search for this C script. See if we find something, some prefetch stuff here. Yeah, here we have a process creation of the C script at this timestamp. Process creation of the C script. And then it's spawning the con host. It's a console application, doing some loading of stuff. It seems to be pretty normal. And here it actually spawns this malware process, and this is interesting. And right after the malware process is spawned, it's creating this network connection as well. But you also see, I think it's the same timestamp, so then it's going to be like completely random how it sends up. But you have a registry entry as well that is created in the users and user Hive, and that like current version run here. So this might actually be kind of interesting to have a look at as well. So let's take a note about this one as well. Software Windows current version run in the user Hive. So we can parse the registry as well, and local machine, you can click into the registry, and it's going to be like pretty much in regedit. You can click around in it. You can also download the Hive files, which are like partially reconstructed only because not everything exists in memory. If you want to run it on other tools, you can click into the users folder, and you see the Dustin Henderson register stuff, and see if we can find in this run key here what it's doing there. And it seems like the malware was creating some registry key here. And it seems like it's actually a registry key in the run folder. It's the persistent model, I believe. It's creating the reg script there. So this malware it might be interesting to know what kind of malware it is and things like this. So we can go into the Explorer, for example. We had a couple of injections there, and we have a folder called Files here. And here, if it has like open file handles, you can actually click in here and just copy the files or partially reconstructed files, a little bit dependent. But if you click into the modules folder, you also see like these injected modules. And oh, here we had some Windows Defender alerts. So let's do a scan with the Windows Defender on AV here. Any other AV will do as well, and see what this malware. It's a hack tool. It's an interpreter, and we could guess that by the name probably. And if you're going to check with the other processes we just talked about, you're going to see the same thing here as well. So let's before we finish, let's do some demo with the Python API as well. I'm going to show you how you can use Python to both search in live memory and do some patching in a quite convenient way. So remember this virtual machine we were using a while ago? I have this notepad document with the super secret password here, and I have like hello HelSec in it. So this is a little bit interesting. So let's have a look at that. So see if we can do something in Python to modify this memory in Notepad to see if we can change it. So I'm going to use start Python. And then I'm going to import the VMMPy Python library. I started it from the MemProcFS folder. And here I have a couple of Python commands you can, Python functions you can call into to do memory analysis. So let's connect to this remote machine. So I'm connecting to this RPC connection and this device HVMM. And we are getting an error here because I need to specify which virtual machine. And so let's specify virtual machine number 6. And now it's connected to the Windows virtual machine. So now we can like retrieve which PID this notepad has, for example, and I'm going to print it on the screen. It's this 8540 PID. And we can retrieve things like the heaps. We suspect the text is going to be located on a process heap. So we retrieve the heaps, and I print the heaps on the screen as well. And this is going to be retrieved as some Python dictionary. And if we want to replace the text in this that we suspect is going to be in this heap, we need to find the text. And in Windows Notepad, the text is going to be in something called UTF-16 little endian, which is like pretty much the text, but it's like every second byte is going to be zero padded. Python has really nice function to do some encoding of the text here. So I'm going to encode the text we want to find, hello HelSec, and print it on the screen. And then we need to replace the text as well with something. So hello Helsinki. Now we can code our small program that is doing like live memory replacement. I'm going to paste it in the screen here. So we're going to iterate over each heap. And for each heap, we are going to be reading its memory. We're going to be reading memory from start of the heap virtual address, and we're going to read the size of the heap. And then we're going to do a find on that memory chunk. And if the find returns something else than -1, which is the error, we are going to be writing to this virtual address, which is the heap base virtual address, plus where we found it in the heap with our replaced text, and we're going to do it in the first occurrence only. I'm going to print something on the screen, so wish me a little bit of luck here. So let's see if it's working. So it seems that we patched something. That's good at least. So we switch to our Hyper-V virtual machine again. See that nothing really changed. And why is that? That's just because I need to be clicking somewhere to update the frame buffer from the notepad. So now we like live modified with this like tiny Python program in live memory on a virtual machine. You could do this using the FPGA hardware as well if you wish. And people actually been using. I was really surprised about this use case. Maybe I shouldn't have been, but I was really surprised because I'm not a gamer myself. It turns out that lots of cheaters have been using the PCILeech and especially the MemProcFS C++ library in order to do hardware cheating with FPGA hardware. And imagine if you're doing like a cheat, you need to have PCI Express devices in your system, right? And so just insert this PCI Express device. You need to have like graphics cards or whatever, and then you can read and write to memory. And if you're only reading memory, you can do things like wall hacks and map decloaks. And if you're going to do read writes, it might be a little bit more easy to detect it. And anti-cheats has been pretty good at detecting this, but then the cheaters change stuff in the hardware setup, and then the anti-cheats cannot detect it, and then it will detect it again after a while, and this has been going on for a while. So I think it's a little bit of cat and mouse there. I don't know which one will like win in the end, but it's like I'm not really a gamer myself, so that's for others to look at. Anyway, when looking forward with MemProcFS, I want to add more functionality, like more analysis tasks, analyze more Windows memory structures. I want to add like DP API decryption of secrets, add more plugins, maybe allow you to use C# plugins as well. Expand this forensics mode background scanning stuff, maybe do hashing of the pages, especially like executable pages. And this would allow me to do some signature lookups against known binaries in a database, for example. That would be pretty awesome, I think. Also, right now, MemProcFS is only going to be parsing like live memory structures. And if, for example, you have a network connection, you might free the memory connection in memory, and it's still like the remnants of it will be floating around in memory. Other memory forensics tools will catch it, but not really MemProcFS, but because it's mostly looking at like active stuff only. And I could add a little bit better detection here. Also recover things like crypto keys, like the BitLocker keys, for example. And really long term, this is going to be a huge job. It would be interesting to add like multi-virtual machine support, because it's kind of common nowadays that you're running virtual machines on your Linux machine, or like Windows Linux virtual machine or other Hyper-V machines on your machine. So it might make sense to parse the memory in several layers. So to sum everything up, MemProcFS is fast, it's easy to use, it's point-and-click memory forensics. Acquisition, you can use either memory dump files, as I shown with the Display Memory Forensics Challenge here. You can use drivers, for example, the Live Cloud KD, but also acquire memory from the local system or the FPGA hardware, and you can also do it over the network. And I do have plugins and APIs for C, C++, C#, and Python, and everything is 100% open source, and you will find it on my GitHub page here. And thank you very much.
Thank you very much, Ulf. That was a very nice presentation.
And pretty much everything worked. I think I've had a small hiccup there, but it's, yeah.
It's good. It's good. We have, I think we have a lot of questions for you.
That's nice. I hope at least it's.
Yeah. So the first question is about the FPGA. Which FPGA card would you recommend for testing Mac targets? A Screamer, M2, or something else?
I mean, Mac targets are really, really tricky. When I did my DEF CON talk, like 2016, Macs were actually working. But I think Apple has been the best vendor in with regards to locking their computers down and securing their stuff against evil DMA attacks. So at this very moment, if you have a like Mac that is not like Mac OS Sierra early versions, which is really super, super old, you're not going to do DMA attacks against Mac targets, unfortunately.
All right. So next question, is there an upper limit for the amount of RAM you can mount with MemProcFS? I know the cases where the RAM size can be also in the terabytes and would otherwise be out of scope for most other memory forensic tools.
I think there are some hard code limits in MemProcFS because I'm doing some sanity checks when I'm starting it to see if it's like if it's a sane amount of memory. I think it's like 1 or 2 terabytes currently. This is something purely in software. If it's a Windows memory dump, because that Windows stuff is what I'm working with, there should be like no theoretical limit for it. So if you do have the need to actually look at a memory dump that is like 2 terabytes big or something like this, and it's not working, like please let me know and I will change this after it's working. And most stuff, like all the find evil stuff, it's going to be running really smoothly and quickly. It's going to be as fast as we did in this demo today. But the forensics part, when you parse the NTFS, that is, of course, going to be like super slow running because it's still going to take some time to read a couple of terabytes of data and parse it.
Yeah, and to be honest, like these cases are like 1 of a million where you have like terabytes of memory.
Yeah, but give it like 1 or 2 years, and I will have it on my home computer, I think, or maybe a little bit longer than that.
Sure?
So
you sure?
Like,
1 or 2 years.
Yeah, like 5, 10 maybe. So, but it's like, but we're getting there. So it's just like like 10 years ago, like.
But at this point, it's not a common thing, even in the enterprise environment. So yeah, but we will get there. Yeah.
Yes.
So how do you protect against or detect this as a blue team? And I think they are referring to the DMA.
Yes, actually, Windows, if you have a kind of recent hardware and you put some GPO settings, or if you have a really nice enterprise Windows laptop, I think they're going to be enabling some protections by default. So it shouldn't be working connecting stuff straight out. So the vendors are actually working on securing this, but it's not really easy for Microsoft doing it either, or Linux guys either, because there's lots of like legacy drivers that depend on DMA, and it might like blue screen the computer and things like this. So it's a really complex matter. It's possible to protect against these kinds of attacks, a little bit depending on which hardware you're running and which settings and which operating system versions and this and that. Or you can buy like one of these ultra portable laptops, which is pretty much just a block of glue or something like this, and it's going to be really hard to disassemble and connect something physically to. But it's a really complex. I can't give you like a straight answer. Do this and you will be fine, because it's so different between different models.
Yeah, of course. Yeah. So, what do you suggest for a mitigation of memory access to make secrets more secure? Moving your hardware to more secure physical location, moving most critical secrets to CPU registers, using external crypto processor modules.
I mean, you can approach this a different way. Of course, like having a physically secure locations, like a data center. I don't think like the DMA attacks are really. It's not a problem there. Really, it's more like for client computers and like servers that are more physically available. And Microsoft and also Linux has been doing things to protect more against stuff like this recently. So if you're going to be running Windows with this hypervisor-based code integrity, I think it is, and the secure kernel, and you have the, like some virtualization of the LSAS, you're not going to be able to actually, depending on the settings in BIOS, being able to read that part of memory where credentials are stored. So it will be, DMA could be blocked that way. by the vendors actually the same way as it blocks if you're running Mimikatz on the live system right now.
All right. So next question. Can MemProcFS connect to multiple computers at the same time?
No, it cannot, but you can run it in multiple instances at the same time. Just use the default is going to mount the M drive, but the same instance cannot connect to multiple computers at the same time, but you can use 2 instances of MemProcFS, just mount on the M drive on one, on the K drive on another instance of MemProcFS. So
maybe you will see a feature request in GitHub in a few days.
Yeah, I have that like long term. I need to do something if I'm going to do like the parsing of the virtual machines as well. But it's going to be a really big job. It's going to be like MemProcFS version 4 or something like this. So it's but I've been thinking in that direction as well. So it's
So next question, is MemProcFS data available in more machine-readable format? For example, good API or JSON formatting, for example?
I have the MemProcFS I have the file system, and the files are as they are at the moment with the forensics mode, I think it is, but it's only going to be like text-based files pretty much there at the moment. I have prepared it for JSON as well, so I could add JSON really easily there, but I'm really unsure myself about which format to use because I'm more like a programmer guy. I'm not really a forensics guy, and it would be awesome if I could get some community input on that actually, so I could add like JSON for that part, or you can actually use, as I mentioned, it's creating a SQLite database in the backend, so you can actually just use SQLite to connect to that database and read tables yourself as you wish, or use the API.
Yeah, based on the who are asking the questions, I would say that here are a lot of forensic guys, so they can actually provide you
so basically then I need a good format, JSON format, which format they want to for this like forensic mode for me to create, and I will add that, and I could do it quite soon actually.
Yeah. All right. So next question. We will have few more before.
Okay, it's good with lots of questions.
Yeah, there is a lot of, and we cannot go through all of them. In this setup. So
I will be at the Discord later on as well. So
So we will take few more, and then we will continue. So would you like to see help in developing MemProcFS? If so, what kind? How would you like to see it used by others?
This is a little bit like tricky question. So far, I've been like developing this myself, and I have received pretty much no contributions for it, or very few contributions. So this also means that I have like the copyright on it, and if I would accept like external, I need to set up some legal agreement shite for it. Unless if you're doing like plugins, then I will like happily accept every kind of plugin you just submit to it. But for the core parts, I need to be doing some thinking about that first. But you can do pretty much everything in plugins, and I think like having like different forensic plugins, I hope I made like a really easy to use API, so you should be able to code your own plugins. I actually had some really nice Python API, Python plugin contributions from a guy called HelSec that contributed something called Pipicats, which is pretty much a Python version of the Mimikatz, which is possible to integrate to MemProcFS. So, and if you do want to create some plugin, I will happily accept it. And if you miss something in the API, I will just add those API functions as well.
All right. Yeah. A few more questions. Could it be possible to use USB for memory dumping? Does it have any profile which would be feasible for it?
For doing DMA, no. it's not really possible. USB itself does not carry DMA, but you have the USB-C, and sometimes the USB-C is Thunderbolt as well, Thunderbolt 3, and then it might be possible to do it. But it needs to be Thunderbolt then for doing DMA.
Yeah. Two questions more. Have you gotten funding from somewhere yet? And do you want to get funding?
Yes, it would be really nice get some funding. I have the GitHub sponsors set up, but it's like a couple of contributors there, so you can actually go and support the project. Or if you want to contribute a little bit larger amounts, or like, because this is my hobby project at the moment, I have a day job, so then we should talk like not here. So it could potentially be quite interesting. Yes.
All right. So second last question. Are there any plans on porting MemProcFS support synaptic storage medium in biological hosts?
I'm like totally gifted to Bill Gates, Microsoft Windows here, so it is like Windows forever. So I think MemProcFS is going to be kind of hard to maybe the HoloLens or something like this, but we'll see.
That was a good one. And the last question, I think it's the best of all. I heard the authors of this OBE Memory Forensics course were awesome. Do you agree?
Yes, I never took that class myself, though. So it's just like, but yes, I know the authors a little bit, and they're like super awesome people. And thank you for inviting me to talk here today.
All right, but that was actually
it was actually a really good class as well, because it must have been because the memory images were really interesting, and it was like super nice to be able to use them here today. I hope I found most of the artifacts in memory, so kind of quickly as well, I hope.
Thank you very much for that. So I think we're done with the presenters here. There is more questions for you, Olaf. So if you could spend some time and answer them on the stream's chat channel, it would be really great. But we will have the closing words in few minutes because I need to finish up my slides. So we'll have a few minute break and then we will continue. And thank you very much, Ulf, for being here with us tonight.
And thank you for letting me to present here tonight. It was really good awesome time. So.
Thank you very much.
Thank you.
Moscow, go ahead.